If you want to stay informed of all the news, subscribe to the channel here. Tesla is creating a massive workforce unlike any seen before, consisting of millions of robots. These robots aren't meant for battle, they're built for labor. While robots have the potential to revolutionize manufacturing, the initial challenge is producing the robots themselves. Tesla's approach to building the Optimus bot hinges on this. For Tesla's robot army to be effective, it requires substantial strength and agility. The Tesla bot isn't designed for simple tasks or entertainment, it's built for serious work. Therefore, Optimus must combine dexterity with raw power, which is where Tesla's expertise in robotic actuators comes into play. An actuator, essentially an electric motor, is something Tesla is highly experienced with. In their cars, electric motors not only drive movement but also manage steering through smaller actuators, especially evident in the Cybertruck's four-wheel steering system, which operates entirely via actuators without mechanical links. However, basic movements like forward, backward, left, and right only involve 2 degrees of freedom, which is relatively simple in robotics. The actuators in the Tesla bot must facilitate a wide range of precise movements, offering over 200 degrees of freedom throughout the robot's body, including 11 degrees in each hand, powered by 6 actuators. The Tesla bot employs 2 primary types of actuators, linear and rotary. Each type has 3 specific designs based on the required action, essentially categorized into small, medium, and large sizes. Starting with linear actuators, also known as screw-type motors, these components are crucial for the sophisticated movements needed by the Optimus bot. Elon Musk favors these linear actuators for their simplicity and reliability. Essentially, they function as motor-driven pistons that extend and retract. Recently, SpaceX transitioned the thrust vectoring control of their Raptor engines from a hydraulic system to electric linear actuators. This switch led to significant improvements in Starship's ability to reach space. Previously, a hydraulic system failure during liftoff on April 20, 2023, caused the rocket to spin out of control and explode. In contrast, the electric thrust vectoring has twice successfully achieved stage separation for the Starship booster. Optimus is applying a similar concept to humanoid robots. For most of the past decade, the Boston Dynamics Atlas has been the benchmark for humanoid robots, utilizing hydraulic power. While hydraulic systems are powerful and widely used in various applications, they aren't practical for consumer products meant for widespread use in homes and workplaces. Electric motors, on the other hand, are quieter, cleaner, less prone to leakage, and require less maintenance. Despite the similarity in mechanical function to human muscles, linear actuators are relatively uncommon in humanoid robots. The original Bumblebee prototype of the Tesla bot primarily used rotary actuators for its arms and legs. The same is true for the new Figure 1 humanoid robot, which also uses rotary actuators exclusively. However, the Optimus bot features linear actuators in key areas: the forearms, thighs, and calves. In these sections, the linear actuators are paired for additional torque, allowing one actuator to push while the other pulls, creating an extra degree of freedom. In the thigh segment, large linear motors operate the Tesla bot's knee and hip joints, which are designed as a 4-bar link mechanism. This design maintains a consistent torque curve across all leg movements, making it more efficient. For example, standing up from a squat requires more force when the knee is bent. A single large rotary actuator would need significant torque in this position, creating an energy-intensive process. Linear actuators and the 4-bar link distribute force more evenly, resulting in a more efficient and linear energy usage. The calf actuators function similarly to the wrists, primarily driving the heel up and down and, when working in opposition, providing a second degree of freedom to tilt the foot slightly from side to side. Additionally, the Tesla bot's foot features a pivot point at the toes, offering another degree of freedom. The Tesla bot's foot doesn't have actuators because there's no need to exert force from the toes unless for activities like jumping or sprinting. Instead, it has a spring-loaded mechanism that allows the toe box to pivot and then automatically return to its resting position. Regarding the rotational actuators, they are similar to the electric motors found in cars or washing machines. The Tesla bot uses permanent magnet motors, which offer more torque in a smaller size and provide a more consistent torque curve, essential for precision control. Though permanent magnet motors are typically more expensive due to the need for rare earth metals like neodymium, Tesla is developing a new motor for the Redwood EV platform that doesn't require these materials, potentially reducing costs for the Tesla Bot as well. The pelvis area of the Tesla Bot prominently features rotational actuators, providing 6 fundamental degrees of freedom. One motor controls the rotation of the torso, and another manages the left-right tilt. Unlike humans, the Tesla Bot can't bend forward at the torso. Forward and backward tilts are managed by 4-bar links in the hip joints, actuated by a linear motor in the thighs. Above each hip joint, a dual motor system controls the sideways angle of the leg for stance adjustments and hip sway for balance, with a second actuator rotating the leg side to side. The shoulder joints also utilize rotational actuators, offering 3 degrees of freedom, one actuator for raising and lowering the arm laterally, another for front-to-back rotation, and a third just below the shoulder for rotating the upper arm left and right. The hand of the Tesla Bot is designed to be as human-like as possible for ease of use, as the world is already designed to be ergonomic for human hands. The human hand, perfected by 3 billion years of evolution, is incredibly sophisticated, making it challenging to improve upon. The Tesla Bot mimics this natural design by using metallic tendons driven by small actuators to move its fingers. Each actuator includes a clutch to prevent the fingers from snapping back, locking them in place when contracted and disengaging to release. Unlike human hands, the Tesla Bot's fingers lack a middle knuckle, connecting only at the hand and fingertip, preventing it from making a tight fist. Additionally, the Tesla Bot has 4 fingers of equal length for manufacturing simplicity. At rest, its fingers curve inward slightly, resembling a human hand. In contrast, the Figure 1 robot has a middle knuckle but keeps its fingers extended when at rest, giving it a more robotic appearance. The Tesla Bot's hand, with 6 actuators and 11 degrees of freedom, requires high precision. Each hand has a small embedded computer controller to drive the fingers and process feedback from pressure sensors in the fingertips, helping Optimus understand hand positioning in space. The head, primarily hollow, contains digital cameras for vision, with 2 degrees of freedom for movement, enhancing its human-like appearance. Inside the Tesla Bot's chest are battery cells similar to those in Tesla vehicles, providing 2.3 kilowatt-hours of storage, enough for a full day, 8 to 9 hours, of operation. Efficient actuators reduce energy consumption and weight, lowering overall energy demands. The battery system, with an integrated computer for power management and Tesla's custom system on a chip, manage sensory input and decision-making in real time, using the same AI principles as Tesla's autopilot software but tailored for interacting with a 3D world. The bot must learn to interact with its environment, understanding objects, shelves, and other elements, a shift from the driving-focused AI. The ultimate goal is to deploy many of these robots to learn from real-world experiences, improving through each mistake, much like Tesla's approach to autonomous driving. In conclusion, the Tesla Bot represents a significant advancement in humanoid robotics, combining cutting-edge technology with insights from natural evolution and Tesla's expertise in electric motors and AI. By using efficient actuators, sophisticated control systems, and high-capacity batteries, the Tesla Bot is designed to perform a wide range of tasks with precision and energy efficiency. As these robots are deployed and learn from real-world interactions, they will continue to improve, potentially transforming industries and everyday life in much the same way that Tesla's innovations in electric vehicles have revolutionized transportation. If you want to stay informed of all the news, subscribe to the channel here.